Let's write a program that rolls a pair of dice 10,000, 100,000 times and keeps track of what are the sum of the two faces of the die as we roll them. And then we're going to compute the distributions of the various sums so that we can get a sense of what's the probability of rolling a 7 versus a 6 versus a 2. And then we'll try and plot this on a chart that looks something like this. So we're going to build what's called a stochastic simulation, which sounds really fancy, but when we get into it, it's just going to be randomizing some trials and keeping track of our results. When you get into trying to solve a problem like this for the very first time, it helps to sort of set up a game plan for where it is you're going to go. And here we're saying, let's try to roll a die a number of times, right? So we're going to have an experiment. And in order to keep track of what we're going to do, we're going to have some list of steps we're going to take over here. So one, we're going to simulate some trials, right? So we need, let's say n trials. Right? So we don't know what n is, but we know that the larger we make n, the more significant our results are going to have, right? The more confident you can be in some outcome if you just keep trying the same experiment over and over again. So we're going to have some number of trials in our experiment, and we're going to need to simulate this. Well, then we start to think, well, what happens in a simulation? In a simulation, we're rolling a pair of dice, and we don't yet know how we're going to do that, but we need some way of simulating the idea of rolling a pair of dice. So let's add a step in here that's roll dice and calculate and track results. Right? So we're going to roll a pair of dice, we're going to keep track of whatever their sum was and do this for n trials. And n might be 10,000, it might be 100,000, it might be a million. The good news about programming and computation is we can choose a really large number and it's the computer's job to go run these simulations. What are we going to do next? Well, if we're trying to calculate the distributions here that we see, notice these are the results from 10,000 trials. What we probably want to do is keep track of the number of times we rolled a 2, the number of times we rolled a 3, a 4, a 5. And so we're going to need to move through all of our results and look at, okay, in this result, did we roll a 2? Let's count one extra tally in the 2's position. Or let's count one extra tally in the 6's or 7's position, right? So we're going to need to count our results. Count outcomes by sum. Rolled sum, right? So we're going to need to do some counting and figure out how many times each of these events occurred in our n trials. And then we're going to try and plot this data like we saw. We could calculate the percentages, and that's actually going to be left as something for you to try. But the last thing we're going to do is try plotting distribution. Right? So at this point, we're going to use some sort of wishful thinking and think that hopefully we can figure out how to navigate these steps. But this is our sort of game plan. And we've taken a problem that's big. We want to simulate this trial and count up some results and plot it. We want to get to the point of plotting, and we're trying to break down our problem into simpler steps. This problem division or decomposition, as it's often called, can help you get started on a problem that you don't yet know how to attack. And I think there's a real value in trying to write out your steps before you get into code. Think about what you want to do, write some code comments, diagram on paper. The more thought you put into how you're going to solve a problem before you start writing code, typically the better results you'll get when you get to the point of writing code. Until you're very comfortable and know all these patterns, the best thing you can do to get started on a problem is write down your steps, think about critically what are the things that you need to do before you get into trying to express those same ideas in code. And thinking first in terms of English, in what we might call this isn't even quite pseudocode, this is more of an overview of the steps we plan to take, and then translating that into code will help you along the way. All right, so let's get into it. I've got a file set up that is a Python file, and I'm just naming this because we're on lesson 23, the simulation Python file. And our goal is to find relative distributions of a rolled pair of dice and plot that result. So what are we going to do? Well, there are a few steps that you might want to take if you're using Pylance to do type checking, which we are in this course. Then I would encourage you to use just basic type checking. We're going to use a plotting library that doesn't have all of the static typing data built into it yet, and this will help avoid some errors. All right, so I'm going to leave that as an exercise. If you need to disable or turn your type checking down to basic from strict, you can do that by pausing the video here and going through it. Otherwise, let's get into it. So one of the first steps that you kind of want to take when working on a new program is going ahead and setting up some infrastructure or some scaffolding that you know you're going to need, right? And we're trying to write a program that runs end to end here from just you start the program and it produces a chart at the end of it. So we're going to set up and use the main function pattern here. So I'm going to have a def main function that will ultimately return none. And this is the entry point of my program, of the simulation, right? So we're entering a simulation here. And maybe what we'll do is write some of these steps down that I've jotted down on paper or here on the screen. So simulate and trials. And I'm not going to write the sub-steps of that. When we get to the sub-steps of simulating some trials, we'll get there. And then we're going to count some outcomes, count the outcomes of the trials, plot the distribution. And so here, we're using some code comments to sort of keep track of what is our game plan. What are we going to do, right? And before we worry about how we might start to make those intents more real, let's go ahead and finish out our overarching pattern here, which is to say if the name of this module when this program is loaded is equal to main, meaning we've tried to run this particular Python module from the command line as a module, then what we're going to do is we're going to call the main function and start up our program. All right, great. So we've got our basic ability to start the program and it's not yet doing anything. So where might we go from here? Well, we may as well sort of scaffold out and use some wishful thinking to generate some functions that we think we're going to need to implement. And so I like this pattern of setting up a main function that has the overarching game plan and then implementing the details of those steps in their own function. So here, let's maybe make a function to simulate our trials, right? So we're going to name a function simulate. And okay, now we need to start thinking a little bit more clearly about what we're trying to achieve here. Well, we know that we would like to be able to have some control over the number of trials we run. So this is hopefully a parameter to this function. So I might go ahead and set up a parameter like n that's an integer. But we should think about what do we want this to return? Well, if we want this simulation to just roll die and keep track of, you rolled 2, you rolled 7, you rolled 6, you rolled 7, you rolled 6, you rolled 3, you rolled 9, like a list of these things, then we probably want a list of the sum of our dice rolls to be returned from this simulation. So I'm going to go ahead and set up a list of type integer. And from here, I'm just going to return an empty list. And we call this the skeleton of a function, where all we're doing is setting up enough of its bones for it to be a valid function. And it will be valid because it returns the right type, so an empty list. But we know we still have work to do. This isn't a correct implementation of this function. We've still got to come back and actually implement its algorithm. But for now, we're just sort of setting up the overarching structure of our program to get a feel for where we're trying to go with this. And I'm going to go ahead and set up a doc comment here, which is roll a pair of die n times and return the results. Return a list of summed rolls. All right, great. So you might notice that we're seeing some red underlines under your type list, and that's because we haven't imported the type definition or the type information about this list type, so we should go ahead and do that. So from typing import list. Okay. And we're using static types here, such as list. And list is a sequence type, meaning we're going to be able to store many different values in it. And list we know is a mutable type, meaning after we set up a list, we'll be able to continue adding more items to it, and we can change its contents. It's not fixed like a mutable sequence is, or a mutable type is. And so we may as well go ahead and keep track of our data here. So maybe our roles is a list of int, and it's the empty list. Right? And we'll return roles. So we still have more work to do, and I'm going to go ahead and fill in some notes here. So notice we kind of, when we were thinking about this problem from a high level, we had already put some thought into what needed to happen in a simulation. We want to roll a pair of dice and track the results, right? So we know that we're going to need to loop n times, but I might just make a comment of that, loop n times, and for each iteration, we're going to one, roll a pair of die, and two, keep track of the results, right? At this point, we now have in our sort of structure of the code that we're working on all of the notes we originally had. So I'm actually going to go ahead and clear those so that it's a little bit less distracting on the screen. So we're using this idea of wishful thinking, right? We still have no clue how we're going to go about rolling our die and keeping track of the results. Or maybe we have some intuition, but we don't yet know the code that we are going to need to do that. However, we can start to feel the structure of this program coming together, and notice that we're trying to implement something that's along the lines of the structure we had hoped to achieve by writing out some notes of the overarching process beforehand. We can actually make one of these comments a little bit more clear here. We want to, from main, go ahead and simulate n trials. We don't yet know what n is, so maybe let's set up a named constant, something like trials, that will be an integer, and I don't know, let's just set this to 100 to begin with. So we know that this is a variable that we can control, or a constant that we can control, and we can rerun this program if we'd like to try a different number of trials in the future. So if we want to go ahead and make this comment real, and a lot of what programming winds up being is setting up, okay, here's my plan for what I'd like to do, and now how can I change this English description into some real code. So I'm actually going to leave that comment there and try realizing that comment below, just below the comment. So simulate trials, and that's going to do that. But notice we're not keeping, we don't have a handle on those on the results of this. We're not storing the value that's going to be returned by simulate here in any kind of variable. So we should probably set up a variable in main to say store the results of the simulation. So maybe I'll set up a variable named results, and its type needs to match the return type of the simulate function, right? So simulate is going to return a list of integers, and so we're going to store that list. Once that function call evaluates, it's going to return to us a list of integers, which we can store in this results variable. All right, that seems pretty cool. Where do we want to go next? Well, here we're sort of faced with this. We've got a number of things that we want to achieve. We should probably keep working on this simulation first. And if we think that we want the process for rolling a pair of die to be something that's nuanced, we could set up a function for it if we wanted. But this is actually something that if we think back, well, how did we generate random numbers? How do we think about simulating the roll of a die? Well, we know there's this randint function. Then randint will generate a random integer between two values, inclusive of both of them. So maybe we'll use randint here. And if we wanted to do that, we could go ahead and import from the random library, import randint, right? So randint is a function that if we want to generate a random integer, we can call that function. Oops. And let me see if I can get this all on one screen. There we go. We can call that function, and it will produce a random integer on our behalf between some bounds. Okay, so we can keep track of the roll here. So roll is going to, and actually I'm going to leave that comment there so that we have this in our notes of what's actually going on. So roll is going to be an integer that is the result of calling randint, and we'll do this between 1 and 6. And we're going to add that with randint also between 1 and 6, and randint is inclusive of both sides of the numbers that you give it in that range. So this would produce a random number between 1 and 6 inclusive. All right. How do we keep track of the results? Well, we've got this list of roles that we're keeping track of. So maybe we should append this role to our list of roles. So roles.append role. All right. Okay, so we've achieved, in theory, these two steps, right? We're generating two random integers, we're adding them together, we're storing that in the role, and we're appending that to our list of roles. But we haven't yet done this n times for each iteration. So when you want to loop n times, now that we know about the for in syntax construct in Python, we can combine for in with a range. And we can do something like for I if we wanted to, or for trial. We're not actually going to need to use this variable, so its name doesn't really matter. For trial in range of say 0 to n, right? And in doing so, we need to be sure to indent all of our code that it belongs in the repeat block of this for in loop. So I'm going to select all 4 lines here and press tab to indent, right? And so we take a look at what we're doing and we see, okay, we're trying to loop n times. And so the way that we're going to get a sequence of n values that we can loop through is with our range sequence from 0 to n. And we're setting up this variable named trial, but we're not needing to use it, right? We just want what's in the body to happen n times. We don't really care about this variable name. We could even, if we wanted to, and you'll see this conventionally done in some cases, we could have named this an underscore to give some hint that, hey, this is sort of a fake variable name we're not going to use. But I think giving it a meaningful name here is totally fine. And I should say for trial. And so inside the loop body, we're rolling a pair of die and we're appending the results to this list. And once we're done with that, we can tell that like we've finished this loop because we've unindented one level. Once we're done with all of that, we're going to return roles. All right. So this feels like we've actually implemented all of our steps here. We're looping n times, we're rolling a pair of die, we're keeping track of the results. This was all of that we kind of had planned for this stochastic simulation. So at this point, it might be a good idea to go ahead and try using this function. And I'm going to open up a REPL, clear my screen here, and I'm going to open up a REPL, and from lessons.ls23 simulation, I'm going to import simulate. And let's see what happens if we try simulate 10 times. So simulate 10 trials, and notice the results we get back: 6, 10, 9, 7, 7, 2, 8, 8, 7, 4. It feels like this is working, right? So this is 10 results, and the lowest value is 2. We're not seeing anything up to 12, so I might try to simulate again, and there we see 12. We could try a bigger number, so we could try 100 simulations, and here we go. We've rolled 2 die 100 times over, and we kind of scan those results, and wow, it sure seems like we really didn't roll many 12s there. We rolled some 2s. I might try 100 more, and there's a 12. There's a 2. And so it feels like we're getting results back that we would expect with 2 die, and we imagine their faces ranging between values 1 and 6. We're not seeing 1 or anything less, because that wouldn't make sense. We've got 2 die, and the smallest number that they can roll is 2 when you add them together. This looked funny to me for a second, 1, but we see that that's just wrapping, right? So if I extended the window here a little bit, we would see that was just that number wrapping around. So it feels like we've got a function that seems to be working. If we wanted to check, are we returning the correct number? We could look at the length of a returned result. So length of simulate 100. And sure enough, when we get back the list of int values from the simulation, there's 100 returned back. So it looks like the simulate function is working, and we're good to continue on from here. And I want to reflect on this idea that we started with wishful thinking. We kind of moved from a position of let's think through our steps, let's write them down, and then let's go try and implement those ideas with actual syntax. And that's a process that programmers from beginners through experts carry out when they're working on new problems that they're trying to solve. But we're not done yet. We still have some more wishful thinking that's been happening in this main function, and we need to figure out how to count the outcomes of these trials and then go plot them. So we can't really plot our counts until we have the counts, so let's actually focus on counting our results first. And what we're going to do is a similar idea. Why don't we set up another function? And I'm going to put this function below simulate. Right? So I'm going to define my function count, and we're going to have some results parameter. Right? So the thing that we're going to count is the results of the experiments. That will be a list of integers. Right? And what is this going to return? Well, let's think about this. If we think about the problem that we're trying to solve here, we're going to get a list that has things like 2, 7, 8, 7, 2. And what we're trying to do is produce sort of a mapping where we count, okay, so our tallies might be, so for the 2's position, we've got 1, for the 3, 4, 5, 6, 7, 8, and I won't go all the way through. We know that we need to keep track of all of these. So for 3, there's none. For 7, we reach the 7, we add a tally here, 1. For 8, we add a tally here, 1. For 7, we add a tally, or we just think about these as numbers and I increase my count to 2, and that's what we're going to do with integer values. So 7 is now 2, and for 2, that's now 2 as well. And you could imagine, if we had another 7 here from our simulated trials, we could increase 7 to be 3, and so on, right? So this is sort of what we're trying to achieve here. We're trying to move through each of our trials, right? We're going to go through this list. That means we're going to iterate through it. So we know that we're going to need some iteration here. And we're going to try and keep track of what was the sum. And there are many ways of trying to keep track of this. And what we're going to try and do is actually leverage the idea of a list and use a list's ability for you to index it by some number, right? So we could imagine that the results here might be stored in a list. So let's say this was 2, 0, 0, 0, 0. And let's imagine that we had 0 and 1 here. Of course, we can't roll a 0, we can't roll a 1, so those values are always going to be 0. But you can imagine that if we had a list for keeping track of our counts, right? So maybe I'll write this out, counts. We could have, the result here would be 0, 0, 2, 0, 0, 0, and I'm going to wrap around here. So 1, 2, 3, 1, 2, 3, 4, 3, 1, right? And if we think just briefly about some of the indices that we're working with here, this would be, because this is a list and we always start our sequences from index 0, 0, 1, 2, 3, 4, 5, 6, and 7, and 8, right? And of course, we would want all the way up through the maximum value we could roll. But the idea here is we can use a list and we can use the index of that list to think of, okay, this is how we're going to tally up the number of rolls that matched this exact same index, right? So to begin with, what we might try and do is set up an empty list of counts for each of our possible roll. And we know that we are never going to roll 0 or 1, but because it simplifies our problem a bit to just start because every list begins with index 0, we'll probably have a list that has extra items in it so that we don't have to do some funny arithmetic to offset the amount rolled with some index that was lower, right? So what I mean by that is we're going to have a list that has indices 0 and 1 in it that are always going to be 0, and we're okay with that because it simplifies our problem. But as we start counting, what we'll do is we'll increase every one of these indices from 0 to 12. will begin with a 0 in it. And each time we iterate through one of our roles in our trials, right, in our results, we'll say, okay, let's go find that index in our counts and increase that amount by 1. And as we iterate through each of our items and carry out this idea of incrementing that index in our counts array, we should have counted up all of our results, and we'll be able to use that array to plot from. So let's see if we can, get back to implementation. So ultimately, we're going to return this list of counts over here, right? So this list of counts is what we're aiming for. So list of integers is what this will return. And let's use some wishful thinking here. So again, we want to establish an empty array, list, I should say. You could think of these as arrays as well, but an empty list for keeping tallies on each result, each possible result. And I spelled this wrong, so establish. Okay, and then we're going to do what? We're going to then iterate through each result and include its outcome in the tallied counts. Right. I probably could have been used a little bit better English here, but we kind of get the gist. This is the process we just tried to think through. We just sort of tried to sketch out in our heads what is it we're trying to accomplish. And again, we need an empty list to keep track of how many times have we seen each of these possible results. We're going to do something clever. We're going to use the index of that list to represent, okay, this is how many times 8 was rolled, is going to be stored in index 8 of our counts list. And then we're going to iterate through each of our items of our results and tally them up. Okay, so let's first take on this first step here, which is we need to establish an empty list. So maybe I name this counts because that's what we used in our example here, where we were saying, okay, these are the counts, and counts is going to be a list of integers that is initially empty. Right? If I wanted to, I could have written out 13 zeros here in order and done that by hand, but let's get some practice writing some more for in loops. And what we're going to say is for let's say possible, we'll just call this I, for I in range from 0, and then we want up to 12 inclusive. So in range, remember, range, the upper bounds, the stop of a range is exclusive. So 13 will not be included in this range. And all we're going to do is say counts.append and 0. Right? So here what we're saying is, okay, we are going through, and we don't really care about this I, right? All we're trying to do is build up a counts list that has 13 values in it. And this is kind of a magic constant, right? So maybe we should fix that and go ahead and fix that. So I might call this max rolls, max roll, and max roll would be 12, but we know that we're going to be exclusive here. So I'm going to say this is +1. And I might go ahead and right here, and I'll move this up to the top in just a moment, but go ahead and define my constant. So max roll is an int constant that would be 12 based on how we're setting up this simulation. And I'm just going to go ahead and select that and move it up to the top under my trials constant. All right. So the reason why we add 1 is because this is exclusive, right? And so we're going from 0 to ultimately 13. But if we later wanted to modify this example to use 3 die and run a simulation with 3 die, we could increase that max roll from a simpler place. And we're going to see that we're going to need that number in some other places as well, most likely. Okay, so we need to go tally up our results. Before we do that, I think it's good practice to go ahead and try and get the skeleton or the bones of your function working. So this is a function that should return a list and currently doesn't. So what list are we going to return? Well, ultimately, we're going to return this counts list, right? What we're saying is, let's set up a list, and that list is the one we were working with here in our sort of conceptualization of where we were going. And we still need to go through and tally up each of our results and keep track of them in this counts list. But ultimately, sure enough, that's the list that we're building up a result in. We're trying to compute the number of times each result occurred, and we're keeping track of that computation in this counts list. All right, so now we want to iterate through each result. When you want to iterate, when you find yourself saying this, like move through each result or process each element in a list or work on each item in a sequence, that's a hint that you can use the for-in syntax, right? So we know that we want to do this on every single item that is in our results list. So what we're going to do is say for item, or I could just call this result in results, right? And we know that with this pattern, that means there's going to be a variable named result available to us inside the repeat block of this for-in statement. All right, now what are we going to do? Well, we want to include its outcome. So that outcome is the result, right? And that is going to be a number that's either, that's 2 through 12. And what we're saying is we want to tally that up in our counts list, right? So counts, and the place that we're trying to tally is going to be the result, right? And what are we trying to do? Well, one way to think about this is we're trying to take the current count or the current tally that's in that index and add 1 to it, right? And we'll simplify this in just a moment with our relative reassignment operator. But just to give a sense of what's actually happening here, this is saying, okay, we've got our counts array. And remember, this starts out at all zeros, right? In fact, now that we've got some sense of where we're going with this, I'm just going to delete some of these notes and try and give this a more sort of a tangible example of what's happening here, right? So we've set up our counts, right? So counts is going to be, I'll just draw it down here, this array, this list where our items are 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. I don't know how many I drew. Let me make that box a little bit cleaner here. Can't draw a box. Okay, one more try. I'm just going to draw 4 lines. There we go. Beautiful. All right, and I'm going to switch colors here to label in our indices. Let me just count these. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We're going to need a few more. Appreciate you hanging in there, struggling through this with me. All right, 11, 12, and 13, and that should be enough. Great. So we index these, right? And to do that, I'm going to just say 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Okay, and this is what we're doing here, right? In this first snippet of code in this function, we're setting up this empty list of all 0 values. So these are the values, or the items, I should say, and these are the indices. Okay, that's the first step. We just want to create a clean slate, and this is where we're going to tally up the results. And then in this next sequence, what we're doing is we're going through each result, right? And so when we think about how do we imagine iterating through each value in a list, well, let's say we're starting with this first value. We would assume that result inside of this body is going to be the value 2. Okay, so how do we think about this line then? So we're saying, let's think about the right-hand side of this expression first. So counts results. This is the same as saying counts at index 2 plus 1. So we look up counts at index 2. That value is currently 0. And so this is 0 plus 1. And we are reassigning that to counts of result. Well, result is 2. That index here, 2, is going to be updated to the value 1, right? And so you can get a sense that we're tallying up in our counts list these results, right? So the next time this loop runs, the computer in the programming language is automatically setting up result the next time we evaluate this line and iterate to be 7. So we look up, well, what is count of result? That's currently 0. We add 1 to that. That's 1, and we store it back in counts of result. Remember, that's still 7, so we would tally up 1 in the 7 item of our counts list. Okay, well, we are iterating through. We're not through every item yet, so we reach 8, and we look up what is counts of result at index 8, and that's 1. Oops, sorry, that's 0, and we add 1 to it. That's 1, and we reassign 1 back to that counts 8 index, right? So that's 1. And finally here, we get to see what happens when we are moving through each of these items when we've already seen one before. So counts of result, again, result is 7. So we're asking what is stored in counts of index 7 and add 1 to that. So we look up counts of index 7 is 1, and 1 plus 1 is 2, which is going to be stored back in counts of index 7, right? So now this is 2. And if we can sort of internalize what this line is doing and say, okay, we kind of get the picture here. Notice that we go back through and result is 2, so that would increase this to be 2, and then result is going to be 7, so we increase 7 one more time, and that would be 3. And then we've reached the end of our results list, and so that loop would complete. And now this function is going to result in returning this list of counts that we've tallied up while we moved through each of these items. All right. So that may have been a little bit of we may have belabored that a little bit, but I think this is such an important concept to understand how we're setting up a list of values, and we're iterating through another list and keeping track of some results in the first list that we set up, and using 2 lists to work towards a common goal. All right. So let's actually try seeing if this seems to work. And so what we can do is go ahead and start up our REPL again and say, okay, Python, I want to, from lessons.ls23 simulation, import count. Great. And we've got this count function. So why don't I try counting? We can do one that was very similar to what we saw before. 2, 7, 8, 7. I don't remember what came next. 4, and then I think there was a 7 at the end of it, right? And we get back this list. It returned to us a list. So let's see if this seems to check out, right? So we've got index 0. Let's see, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And what do you know? So we had a single 2 here. That's 1. We had a single 4. The 4 index is also 1. And we had 3 7s. So 1, 2, 3, lucky 7s. And 1 8. And it looks like this actually did work. And if we wanted to see, well, okay, can we actually use these 2 things in conjunction with one another? I might try and import my simulate function. And remember, simulate, we give it the number of times we want it to run. And let's say we want to count up that result. So we're going to count the result of simulating, I don't know, 100 trials. And we get a response that seems to add up, right? There's never going to be a result that's in index 0 or 1, because you can't roll 2 die that are faced with 1 through 6 and sum to 0 or 1. But the rest of those, it seems like, yeah, that seems to check out and add up. So we could try it with 1,000 rolls, and we get the point in the sense that, yeah, it seems like this looks like it's working. We could do a little bit more checking to convince ourselves, but I'm going to claim that this gives us enough confidence to keep moving on in our problem. So we've got our count, and in our main, where we sort of had the overview of the problem we were trying to solve, maybe I'll set up a variable named counts that's going to be a list of integer that keeps the result of counting up all of our results. And what we're trying to do is count our results, right? So our English said count the outcomes of the trials, and we know that we wanted to keep track of that so that we could go plot that later, right? So now we need to plot a distribution. Well, plotting is a lot like printing. We don't expect there to be something that gets returned to us in our program. We just want to make some results show up on the screen. So we're going to use some wishful thinking again and say, okay, well, we want to plot our counts, right? That's what we're trying to plot in this particular program. We haven't yet written the function named plots. We're using some wishful thinking, but I'm going to go ahead and drop this in and let's go think about the function that we need to write. And we know already that it needs to take in a list of int values in order to work, right? So I'm going to come down and below counts, define a function named plot, and it's going to take in our counts, which is a result of, or is a list of integers, which are our tallies. And this is a procedure that returns none. And we're going to say plot the results of our simulated experiment in a bar chart, in a histogram. Right? So we've done the work of turning this into a histogram in our counts function. We're bucketing each of the results from our trials into the sum. And now we just want to create a plot. Well, we're going to briefly work through an example of plotting using a library called matplotlib, which should have been installed already through some steps you took earlier. It's a library that you can install through a tool called pip, which we'll explore as well soon. But this was a step that you took early in the semester. And so I'm going to go ahead and import from matplotlib. I'm going to import pyplot. Right? And pyplot is an API, which stands for an application programming interface. It gives us a set of functions that we can use in order to make plots interactively and programmatically in our programs. Right? So we're going to try and dynamically make a plot using matplotlib's pyplot library. Now, when you do things like plotting, it's not uncommon that you want to look up and use reference for how is it that I achieve the plot that I wanted to set up. And when you're using a library like this, it's very common that you're going to look for examples in the library's documentation. And I'm going to use a simple example that we found on the pyplot website and in its documentation for setting up this bar chart. So when you set up a plot, you typically want to have a title, right? So pyplot dot title, and this sort of function, the way we're using this as a function call to a module, and this looks a lot like a method call, is just a convention that we're using with the pyplot library. And what we're going to say is maybe distribution of rolled values. This will be the title of our chart. You always want to have a title. And then we think about, well, what do we want our x-axis to be? And our x-axis is going to be the summed value of the rolls. So maybe pyplot dot x-axis, or sorry, x label is sum of roll, and pyplot dot y label is the frequency. Right, so we're not actually calculating percentages here, and that's actually would be a very good practice exercise. See if you could take on one more step here, and now that you've bucketed all of these, can you count the percent likelihood for each of these sums and come up with a new list of those results? But we're not going to go that far. And now we want to set up a bar chart, right? So pyplot.bar. And one of the things that I should just go ahead and make a caveat of is you see some red underlines here, and you may see that in yours. This is an example of a library whose type bindings aren't fully specified, and we're going to ignore this as a problem. We know that creating a bar chart is built into this library. It was in the website that documented this library, and so we're going to use that same example here. And in this case, for using this library matplotlib, we're going to ignore any type warnings we get as a part of them. So when we plot a bar chart, we need to give what is our x-axis, and then what are the values along the x-axis, and then what are the magnitudes of each value in that axis, right? So what's our axes for x? Well, we might go ahead and set up a range for that, right? So we need a sequence here. So we're going to say x-axis values is a range, and it's a range from 0 to, well, we set up a variable for this, right? Max roll plus 1 is the last part of that range. So I'm going to say x-axis values is the bar function needs a list or a sequence of its x-axis values, and then it needs the y-axis magnitudes. So counts is what we're trying to plot, right? This was the result of the previous function we implemented where we counted up the frequencies of each result, and that's going to inform the magnitudes that we map to for each of our x-axis values. And the last thing we're going to do is say pyplot.show, and that is a function that will cause the pyplot chart to show up, and we can see the results. So now we should have effectively a working program here. There's no more wishful thinking that we need to implement. Again, the level of detail when you're working with a library like a charting library, it's very frequent that you're going to be referring to documentation. I don't remember all of these exact names. Like I would have probably said X title by default, but it's X label. So some of these distinctions are things that are details that you don't, unless you do this every day of your life, you're not going to commit to memory, and you'll refer to documentation to look up, right? So let's try running this program, because if we think about what happens, right? In main, we simulate our results, we count them up, and then we plot them. And through sort of refining and digging into each of these problems and starting to add more specificity to it, we got to the point of, okay, well, if this all works, then we should see a plot when we go to run our program. So now, rather than starting a REPL, I'm going to try and run the simulation as a program. So python-m lessons.ls23 simulation. And what do you know? We've got a chart here that looks like, wow, it's not quite what we expected. But one of the things that you know about probabilities and simulations is there's going to be some unexpected outcomes if you have very few trials. And the best way to get more confidence in a distribution or an experimental setup is to increase the number of trials. So this was something we set up as a constant. Let's try this one more time. So I'm going to go back up to the top, and we had 100 trials. Well, let's drop some zeros in there and maybe have 100,000 trials instead. And we're going to run the simulation one more time. So that takes a little bit longer to compute, but wow, computers are incredibly fast. And look at that. We actually get what feels much closer to the expected type of distribution. Like we think that there are the most ways that you can roll a 7, or of the possible combinations of die, 7 is the most common or the most likely result, and that shows up in our chart here with the center of this distribution. Whereas 2, there's only a 1 in 6 chance for each of the die to roll a 2, and same with 12, and so those are the least likely rolled outcomes. And so we can get a sense that, wow, after simulating this more times and giving our computer a chance to sum it up, the sort of the noise of having very few and the lack of confidence and having very few trials in a simulation gets washed out, and by simulating more trials we get a much better result that we can be more confident in, right? So in this video, in this lesson, we took a very intentional strategy. We started by writing out what is our overarching set of steps that we think that we're going to need in order to solve our problem. And we started filling in some of those blanks in places in our code. We used some wishful thinking, right? We started with comments that wouldn't do anything on their own, but it gave us sort of a plan of attack for making progress. And we started to sort of work our way through from the start of our problem to the end of it. And along the way, we set up some functions that sort of encapsulated different parts of this process, right? So the simulation step had its own function. And once we finished a function, we were able to test that and gain some confidence that, yes, it seems like this function is working. And we can now consider that challenge abstracted away and focus on the next part of our problem. This strategy is really important for when you're trying to attack a new problem. And it won't necessarily go quite as cleanly as it did here. This was a program that I have written before, so I kind of knew the overarching steps. But what I'll tell you is when I attack a new problem for the very first time, this is exactly what I try and apply to it. And sometimes you'll realize, oh, I missed a step somewhere, and I need to go back and think about doing something before this point. And that's okay. But trying to put a high-level picture into place and a high-level plan and slowly chip away at making that plan more concrete in code is highly, highly encouraged. And here we saw, using lists and some functions, we can start to calculate and compute really cool simulations and work with lots of data, right? So in our program, we at one point, after running simulate 100,000 times, we had a list that had 100,000 integers kept track of in it, right? And we generated 200,000 random numbers in order to produce that. And then we computed over 100,000 of that list of 100,000 results and bucketed those results into an array that had some counts, and we tallied them all up. And we start to think about, wow, the scale of the computation that just happened here. If you imagine trying to roll a pair of dice 100,000 times and keep track of how many times you rolled each combination, it would be painstakingly boring. But with this, we've got really interesting ways, and with computation, we've got really powerful ways of creating simulations that allow us to get a sense of probabilities of even more complex problems than this, weather patterns, voting outcomes in national elections, things like this, and try and have a better sense of the distributions of possible outcomes. Great work in this lesson.